Good evening, everyone, and welcome to the third session in our amateur radio technician class. Certainly hope that everyone had a good holiday yesterday in Trinidad and Tobago. It was Corpus Christi, and trust that you're well rested from today's activities as we get right into our session number 3. A couple of questions from our last session that was asked via email. We will deal with very quickly. The first one is that the exam fee of $100 TT that was noted in session number 1 is actually not to do with the attendance of this class. There's no cost to attendance of the training session. The $100 exam fee is after you have finished this class and you decide to take the exam, the actual amateur radio exam. That fee is paid to the volunteer examiners. So again, just to clarify, there's no cost to attend this training program. So just to give an idea of where we are, on your screen is the list of topics that would be part of this course. And just thought I would visually demonstrate where we are so far. Now that we have had 2 sessions, an introductory session with a little bit of the material, and a second session that we started to go a bit more in depth, and we are now into our 3rd session. We are still on the first topic, or the first item on the curriculum, which is electrical principles. So that's where we are. But we have all the way to go to finish this course by looking at electronic components and circuit diagrams, followed by radio wave characteristics, antennas and feed lines, amateur radio signals, electrical safety, amateur radio practices and station setup, station equipment, operating procedures, and rules and regulations. So from time to time during the course, I'll bring back up this slide to show you where we are as we progress. So just gives you an idea of the curriculum. Last class, we looked at an aid to remembering the Ohm's law formula called Amor's plate. We dealt with the application of Ohm's law, how we do calculations to calculate resistance, current, and EMF or voltage. We dealt with what's the difference between a series and a parallel circuit. We also started to look at the power formula, or the DC, direct current power formula. Yeah. So I want to thank you for staying with us thus far. Congratulations to you. And just remember, you can in fact have a look at the recordings via the YouTube channel. And I will just take a minute to mention, best effort is being made to provide the recordings to you. We are unable to guarantee that we will always have the recording available. So that's why we recommend ensuring that you attend the live course, just because technology sometimes doesn't always work out. So just bear that in mind as we progress in our course. So let us pick up where we left off last session. So you should have on your screen at the moment the No Nonsense Guide, page 11, if you're following with the book, or if you're just following on screen. Let me see if I could make this a little bigger. Yeah. You know, some persons might be using a mobile device. So we left off with the mention that you can manipulate the power formula to come up with any of the terms that you need to solve. Just as with Ohm's law, the power formula can be manipulated in the same way. And what is the power formula? Well, if you recall from last class, we said power is equal to the voltage or the EMF multiplied by the current. That's the power formula, or the DC, direct current power formula. And we need to learn this formula. Let us deal with one more question in respect of that formula, and it has to do with manipulating the equation P is equal to IE to another form. So let's have a look at that. The question and the question pool is, how many amperes are flowing in a circuit when the applied voltage is 12 volts DC and the load is 120 watts? So what are they asking us in this question? They're asking us, how many amperes are flowing? Now, you know that the unit of current is the ampere. So when they ask you how many amperes are flowing, they're really asking you what is the current. So they're asking us to find the current. So therefore, we need a formula that says current is equal to something. So that's what we need to find out. But they have also given us some information. They have told us that the voltage is 12 volts DC, and they have told us that the load is 120 watts. So 12 volts DC is the voltage, and 120 watts, that's the power, because we know that the unit of power is the watts. So they have given us voltage and the power. So all we need to solve for is the current. But if we look at our power formula, we see P is equal to E multiplied by I. When we manipulate algebraically, we end up with I is equal to P divided by E, or I is equal to P over E. So all we need to do once we have moved around the terms to solve for I is to plug the information into the new formula. I is equal to P divided by E to solve for I, which is the current. Because they have asked us how many amperes are flowing, we need to find out the current flow. So if the voltage is 12 volts and the load is 120 watts, we plug it into the formula as we see here. 120 watts divided by 12 volts. Well, a fairly straightforward. 12 into 120, we get 10 amps or 10 amperes. And notice the various ways they write things, right? In the formula 10A, 10 amps. So the answer is 10 amperes. Again, a straightforward application of the power formula. Only three things inside of there, at least in the standard power formula. P is equal to E multiplied by I, and you can solve for any one of those. So that was just to wrap up our power formula. And we now move on to units, conversion of the electrical units. Now this should probably sound very familiar to you, this next topic, because they're telling us here about the prefixes to indicate the order of magnitude for any units. Milli is the first one. We would have encountered milli when we are measuring something. We may be measuring the width of our thumb or the width of a pencil, and we may say it is 5 millimeters, millimeters. We may be measuring something very tiny, and we may find out that it's 60 micrometers. Even smaller, we may measure something and find that it is so small that we have to say it is in picometers, right? And if we are driving any distance in a vehicle, we may say it is 10 kilometers, or let's say kilometers, right? And then we have the mega quantity, mega, right? And when we have another larger yet still multiplier, giga, all right? So all of these are prefixes that we will have a look at in this table in order of magnitude. Pico being the smallest, and as we go up in size, we go to nano, larger yet micro, even larger yet milli. And we go into the big guns now. So kilo, followed by mega, and then by giga. As we go up this table, we get larger. As we go down this table, we get smaller. All right? So it's important to know the abbreviations. For giga, it's the capital G. For mega, it's the capital M. For kilo, it's the lowercase k. Milli, it's the lowercase m. Now notice that mega is capital M, but milli is common M. So if you make a mistake and put the small m, you're talking about a very small amount. When you use the bigger M or the uppercase M, it's a large figure. And the micro uses the symbol mu, or you can just type the letter U in place of it, but it's really the Greek letter mu. Nano is N and pico P. So these are the abbreviations for these prefixes. But the question is, what does a prefix mean when we put it in front of a term? So before we were talking about millimeter, micrometer, kilometer. So let's take kilometer. We may be familiar with the term kilometer in terms of a distance. When we say it's a kilometer or a kilometer is 1,000 meters. If you like exponential notation, it's 10 to the power of 3. But if we say it's a millimeter, it is 0.001 of a meter. So that is what the prefixes mean when we apply it to some unit. But in amateur radio, we will be interested in electrical terms. So you will see those terms that we talked about earlier, like watts, for instance, or volts, or amperes. You will see these prefixes applied to those terms. So while we were dealing in volts earlier, when we're talking about thousands of volts, we will say kilovolts. So instead of saying 1,000 volts, I will say it's a kilovolt, because 1 kilovolt is 1,000 volts. Yeah? In terms of watts, same thing. If I have 1 watt, it's 1 watt. But if I have 1,000 watts, instead of me saying 1,000 and writing out 1000, instead of saying 1,000 watts, I can just say it's 1 kilowatt. Yeah? So, you know, when we're dealing with very large numbers, we can use these prefixes to shorten the number that we write down. But we say 1,000 watts is a kilowatt. But let's look at a milliwatt. What is a milliwatt? A milliwatt is 0.001 of a watt, a very small number. We could even go to a microwatt, 0.00001 of a watt. So very small. So these prefixes on top are large, and the prefixes below are small. So let's deal with a question in the question pool that deals with the prefixes. The question is, how many milliamperes are in 1.5 amperes? So look at what we are converting from. Milliamperes is what they're asking about, and they have given us the amperes. So if it is that we need to find out how many milliamperes, we need to multiply by 1,000. Why do we multiply by 1,000? Because 1 ampere is 1,000 milliamperes. All right? So they tell us here to convert amperes to milliamperes, you multiply by 1,000. And the converse is also true. If we had milliamperes and we wanted to find out how many amperes, we divide by 1,000 to get to the ampere. So the answer is we take the 1.5 multiplied by 1,000 and we get 1,500 or 1,500 milliamperes. Let's look at another example. So it doesn't matter whether we're talking about volts or watts or even terms that we haven't come across yet in our course. The concept remains the same. Once we hear kilo or milli or anything else before, we should not get confused. We just need to be mindful as to the multiplier or how many of one it takes to convert to the other, or what do you need to multiply by or divide. So they're asking us this question. What is another way to specify a radio signal frequency of 1,500,000 hertz? So again, a very large number. But remember earlier when we said, instead of saying that I drove 1,000 meters, I can say I drove 1 kilometer. That's what we're doing here. Instead of saying that my frequency is 1,500,000 hertz, what I do is let me make it smaller. I see here that I know 1,000 of anything is a kilo, right? So I can convert this here by dividing by 1,000 to bring the number down to just 1,500. And I know when I divide by 1,000, that's a kilo. So if I divide 1,500,000 by 1,000, I get 1,500. But that will be 1,500 kilohertz because I converted from hertz to kilohertz, just like I convert from meters to kilometers. I am driving 1,000 meters. It's the same as saying I'm driving 1 kilometer. If this were meters, if they told me I was driving 1,500,000 meters, right? I can simply divide by 1,000 and say I'm driving 1,500 kilometers. So don't let the term that you might not have seen yet be confusing. They're just simply trying to convert using the prefixes. So 1,500,000 hertz, it's the same as 1,500 kilohertz because we divided by 1,000 to go to the larger notation. Let's do another. They make the note here that says that's what we just did. We divided by 1,000. So let's look at another question in the question pool. I will again remind the class that after every question, there is a number in brackets. This is the question pool number. Perhaps a little later on or in another session, we will actually look at the question pool and convince ourselves that this is the question number. You can always refer back to the question pool. Next question. How many volts are equal to 1 kilovolt? Well, we know that a kilo anything is 1,000 of it. Kilo, 1,000. So how many volts are in a kilovolt? Well, kilo being 1,000, we simply say 1,000 volts. Let's ask another question. How many volts are equal to 1 microvolt? Well, let's look at the table again. How many volts equal to 1 microvolt? Look the answer right here. A micro of anything is 0.000, well, 5 zeros and a 1, all right? So if you divide by 0.000001, you are dividing by 1 million. So the answer would be 1 millionth of a volt. It's really about shifting the decimal place. So you take 1 and you shift it 6 places, you'll get 1 million. Okay, so 1 millionth of a volt. They make the note here to convert, right, so they're just telling you here to convert from kilovolts to volts, you multiply by 1,000. To convert microvolts to volts, you divide by 1 million. So it's really about shifting and determining whether you want the notation in a smaller prefix or a larger prefix. The next question, which of the following is equal to 500 milliwatts? So let's look at that. Milliwatts. A milliwatt is 1,000th of a watt. So if 1 milliwatt is 1,000th of a watt, that means that if we want to find out how much is 500 milliwatts, one easy way to look at it is, if I were to multiply this by 2, and I'm just showing a little technique here for quick calculation. If I were to multiply this by 2, I get 1,000 milliwatts, right? Which is 1 watt. But I'm multiplying this by 2, which is 1,000 milliwatts or 1 watt. But if I only want to find out about 500 milliwatts, 500 milliwatts is half of 1,000 milliwatts, right? So if 1,000 milliwatts is 1 watt, what is half of a watt? 500 milliwatts. So these are the types of conversion questions that they will get you, that you'll have to practice doing. And they let us know here that to convert from milliwatts to watts, you divide by 1,000. So we want to go from 500 milliwatts to watts. We divide 500 by 1,000 and we get 0.5, which is the answer, 0.5 watts. Again, don't be fazed if they were to introduce terms that you have not yet heard about. Think of meters and kilometers. How many microfarads are equal to 1 million picofarads? So let's look at that in terms of the table that we have here. So we're going from micro to pico, right? So micro to pico. So notice that pico is smaller than micro. And the question is, how many microfarads are there in 1 million picofarads? So let's go back to the table. Microfarads to picofarads. The difference is 6 decimal points. 6 decimal points, if you were to convert it to whole numbers, would be 1 million. So if it's 1 million picofarads and we convert, we will get 1 microfarad, because 1 million picofarads is equal to 1 microfarads. How we get that? The order of the multiplier between micro and pico is 1 million. If you want to go from micro to nano, that's 1,000. If you want to go from nano to pico, that's another 1,000. But if you want to go from micro to pico, that's 1,000 multiplied by 1,000, which is 1 million. So every time you go down in the units here, you are going down by a multiplier of 1,000. So if you skip 2 steps, it's multiplied by 1,000, multiplied by 1,000, 1 million. Or you could say divide by 1,000, divide by 1,000, you're dividing by 1 million. It depends on whether you're going up and down, up or down, you multiply or divide. But the point is, to go from one term to the next, you're multiplying or dividing by 1,000. And if you want to go from one term to the next term, you're multiplying or dividing by 1 million. So again, the question is how many microfarads is equal to 1,000 picofarad? They tell us here that there are 1 million picofarads in a microfarad. And that's the answer, 1 microfarad. They do also tell us the term that we have not yet been introduced to, which we'll be coming up to shortly, is that the farad is the unit of capacitance. We will deal with that later on. Let's do another question. We'll take a break in a couple of minutes' time. If an ammeter calibrated in amperes is used to measure 3,000 milliampere current, what reading would it show? So we are looking at 3,000 milliamperes and we want to convert it to amperes. So we need to get the reading in amperes, but we are measuring something that is 3,000 amperes. So we need to go from milliampere to ampere. So we wonder, what do we have to divide by to go from milliamperes to ampere? So let's look at the table again, milliampere to ampere. So milli, right? So how much do we need to divide by to go from milli to the base unit? The answer is 1,000. We have to divide by 1,000 to go from milli to the base unit. It's the same way if we had something that was 1,000 millimeters and we want to know how many meters, we divide it by 1,000. So 1,000 millimeters is equal to 1 meter. So we divide by 1,000. We're just dealing with amperes in this case. So if it is, we have 3,000 milliamperes and we want to go to amperes, to go from milli to the base unit, we divide by 1,000. So 3,000 divided by 1,000 is simply 3 amperes. Okay, let's move right along. So they're asking us a question. Again, we have not yet dealt with the unit called the hertz, but they're asking us, what is the proper abbreviation for megahertz? So the unit of frequency, the hertz, it's measured, well, the symbol is H, capital H, lowercase z for hertz. but they're asking us is what is the proper abbreviation for megahertz. So for this lesson, what we are looking at is what is the prefix that we use when we saying mega something. So if we were saying a megawatt, it will be mega, large M. So a megawatt will be large M followed by a W for watt. Similarly, they are asking us that question. What is the proper abbreviation for megahertz? So the prefix has to be capital M. And later on, we will deal with what is a hertz. And we will find out that HZ, or capital H lowercase z, is how you represent hertz. So the lesson here is that mega uses the prefix capital M. If a frequency display calibrated in megahertz shows a reading of 3,000, this is a decimal point, 3.525 megahertz, what would it show if it were calibrated in kilohertz? So let's look again. We are trying to move from megahertz to kilohertz. So you see how they're mixing it up for you here, trying to confuse you? They show you megahertz written this way here, and they write out the kilohertz. But the focus of the question is megahertz to kilohertz. So we need to find a way or something to multiply this figure by to go from megahertz to kilohertz. How do we know what that figure is? Well, we come back to our trusty table. And look, we have it right here. Kilohertz to megahertz. To go from one of these terms to the next, it's 3 decimal places. So a megahertz is 1,000 kilohertz. To go from one to the next, the multiplier is 1,000. Yeah? So we apply that knowledge to the question and multiply 3.525. We multiply that by 1,000 because we are going from megahertz to kilohertz. We multiply by 1,000. And when we do that multiplication, 3.525 multiplied by 1,000, we shift the decimal point 3 places, 1, 2, 3, and that gives us 3,525. Next question, which of the following frequencies is equal to 28,400 kilohertz? Now they will give you a table showing you all sorts of variations of this number. But the correct answer, so they will try to trick you. But the correct answer that we are looking for, it just so happens that the correct answer is looking for megahertz. So how do we convert kilohertz to megahertz? Well, if above we converted from megahertz to kilohertz by multiplying by 1,000, if you recall, when we went the other way, we multiplied by 1,000. We went from megahertz to kilohertz, so we multiplied by 1,000. But if we are going from kilohertz to megahertz, we divide by 1,000. So 28,400 divided by 1,000 is, we shift the decimal point 3 places, 1, 2, 3, and we get 28.400 megahertz, which is the answer given. Let's deal with this next question. If a frequency display shows a reading of 2,425 megahertz, what frequency is that in gigahertz? So what they're really asking us to do here is convert from megahertz to gigahertz. So let's look at our trusty table once again. and look at megahertz or mega prefix and giga, the giga prefix. How do we go between these two to convert from one to the other? Well, we either divide by 1,000 if we are going up, or if we're coming down, we multiply it by 1,000. So we are going to do just that in our question that asks us to go from megahertz to gigahertz, and we are going up. So because we are going up, we divide. So 2,425 divided by 1,000, again, we shift the decimal point 3 places. 1, 2, 3. So decimal points ends up between the 2 and the 4. So you get 2.425 gigahertz, which is the answer. So at this time, let us take a little break, 2-minute break, and we return at about, let's say, 8 minutes after 9. Okay, we'll start back in 1 minute's time. Welcome back after a very short break. So we move on to the topic of decibels. Decibels you will encounter in the amateur radio world because that is a measurement you will see used for several things, and we must understand what the decibel is. Now, the decibel itself is not a unit, it is really a ratio, and it should be used with respect to another unit. A ratio is saying that my power level, I just increased it twice. So that's a 2-to-1 ratio, for instance. Or I just increased my power level of my radio transmitter 10 times. Or I am moving my transmitter power from 10 watts to 100 watts. So my power increases 10 times. You know, I'm multiplying my power. Or I've just doubled my power by going from 5 watts to 10 watts. All right. But when we talk about the ratios, because of the very large numbers sometimes we deal with in amateur radio, we often use the decibel to express the ratio between the values. So for the purpose of this course, we don't really need to know the formula, and that's what the text is saying. But guess what? We like to give you something extra in this class so that you have a little fun. So we will actually show you the formula to calculate how we calculate decibels. So when we say it's a ratio, you have a little idea. So I'll just take a minute or so to show you the formula in a little bit. But let's go through the questions associated with the decibel, and then we will look at the formula, all right? So you need to know a couple of things for the purpose of the exam. The first thing is that the decibel scale is such that when the number is positive, it means that you are increasing the power, right? When the value is negative, you are decreasing the power. So the actual value itself wouldn't tell you whether you're increasing or decreasing. You need to look at the sign, either a positive sign, which is simply indicated by, well, nothing at all, or a negative value, which means that you put a minus sign before the figure. So there are a couple of decibel values that you need to know for the exam. The first thing that you need to know is that you will be given one power level and another power level, and what you need to look at is whether it's increasing from one to the next or decreasing from one to the next. So that will give the sign. And then the next thing you need to look at is it twice the power? Is it 4 times the power? Is it 10 times the power, for instance? Or it could be the other way around. Is it half of the power? Is it quarter of the power? Or is it 1/10 of the power? And so on. So you're getting a question that will tell you you're increasing power levels from one to the next. You need to look at the relationship between those two values. So the values for decibels that we'll be concerned with for this course are 3, 6, and 10. Why these 3 numbers? Well, it just so happens that 3 decibel represents a value or an increase, if you're increasing, of twice times. So if you go from one power level, let's say 10 watts to 20 watts, because you are increasing twice the amount, that is equivalent to 3 dB. Simply need to learn that. Again, we will show you the formula how you get that 3 dB, right? 6 dB. Well, 6 dB is simply 4 times if it's positive, or 1/4 if it's negative. So if we say that we have increased the power by 6 dB, that means we are multiplying the power by 4. If we say that the power level is negative 6 dB, then we have just multiplied that by 1/4 or divided by 4. And the next decibel value that you need to learn what it means is 10 dB. And 10 dB is simply multiplying by 10. So if you have increased your power level by 10, that's 10 dB. If you have decreased it by a factor of 10, 1/10, that is minus 10 or negative 10 dB. Before we go into the questions, I promised you a little session on the formula to see how we get those numbers. All right, so the material noted that we don't need to know the formula for decibels, but there are persons who may be curious, how did we end up with those ratios? How did we end up with 3 and 6 and 10? So the formula for decibel, to determine the decibel for power, it's 10, the number 10, multiplied by the logarithm, and this is to base 10 of the power number 2 over the power number 1. So you take the two power levels that you are going from to. So let's say you are at 2 watts and you're going to 4 watts. You put 2 on the bottom and you put 4 at the top. When you do that, you divide it. And then now you take the logarithm to base 10 of that value. And then you multiply it by 10. And that is how you come up with the dB value or decibel value. Right? Strictly speaking, if it's with respect to a milliwatt, we'll be dBm. If it's decibel with respect to a watt, it'll be dBW and so on. But let's look at some examples. Right. So let's look at the questions and then we'll come back to that little diagram and we will see the workings for how we came up with the answers. So the first question that they ask us about decibels is, what is the approximate change or amount of change measured in decibels of a power increase from 5 watts to 10 watts? So notice they're asking us for decibels. And they're telling us that it's the power increase. So notice the increase. And as we learned earlier, if it's an increase, we get a positive decibel value. And we are going from 5 watts to 10 watts. That means we are doing what? We are doubling the value. From going from 5 to 10, that is doubling the value. So we learned earlier that if we double the value, it's 3 dB. And here's the answer. So we will learn it by rote for this, right? But I will show you the formula, how we got it back in a little bit. And they just note here that 3 dB corresponds to a ratio of 2 to 1. Because we are going from 5 watts to 10 watts, it doubles the power. And we can also say that there's a gain of 3 dB. Let's go to the next question. What is the approximate amount of change measured in decibels of a power decrease from 12 watts to 3 watts? So notice in the question, they want to know the decibels, that's what they're asking for, how many or how much decibels. Power decrease. So once you see decrease, you know the answer has to be negative or minus. So in the question pool, one of the distractors might, or several of the distractors may be positive. So from the time you see that, they're asking about a decrease, but you've seen positive values, you will say, nah, man, decrease can have a positive value. It has to have a negative value. So what are we going from to? We are going from 12 watts to 3 watts. So going from 12 watts to 3 watts, that is a quarter. And as earlier mentioned, multiplying by 4 or dividing by 4 is 6 dB. So that's the answer, 6 dB, but not just 6 dB, minus 6 dB. Why minus? Because it's a power decrease. If it were a power increase, if we were going from 3 watts to 12 watts, then it would have been 6 dB. But because we are decreasing from 12 to 3, we are dividing it by 4, which is a quarter, or a ratio of 4 to 1. We get 6, but minus 6 or negative 6 dB. And they simply say here, this is what they're asking us to learn by rote. 6 dB corresponds to a ratio of 4 to 1. And a decrease in power from 12 to 3 watts is a ratio of 4 to 1. And because the power it's a power decrease, the value is negative. Okay. What is the amount of change measured in decibels for power increase from 20 watts to 200 watts? So again, they want to find out decibels, but they're asking us here now for power increase. So you know, or we know, that once it's an increase, it's going to be a positive answer. What are we going from to? We are going from 20 watts to 200 watts. To go from 20 to 200 is a ratio of 10. So because it's a ratio of 10, we learned earlier that once it's a multiplier or a ratio of 10, it has to be 10 dB will be the answer. But is it positive or negative 10 dB? Well, they tell us it's an increase. Again, we just repeated it. You know it's going to be a positive value. If we were going from 200 watts to 20 watts, which is 1/10, still a ratio of 10 to 1, but 1 to 10 really, then it would have been minus 10 dB. But because we are increasing, it's plus 10 dB. And that's what the note tells us here. Increasing the power from 20 to 200 watts is a ratio of 10 to 1, a reduction, an increase in power. And therefore, because it's an increase, it's 10 dBs and it's a positive value. So let's go back to the little formula so you can see how we got the 3 dB, how we got the minus 6 dB, and how we got the 10 dB, so that you at least see how it's calculated and constructed. Remember this formula here for decibel calculation, where we multiply 10 by the logs of the second power over the first power, or P2 over P1. So using the question that we just dealt with, the first question told us that we increased the power from 5 watts to 10 watts. So 5 was P1 and 10 was P2. So 10 divided by 5 is 2. So we come down to this equation now, right? It was 10 multiplied by the log of the power 1, power 2 over power 1. We substituted for power 2 and power 1. And we end up with 10 multiplied by the log of 2. So what we need to do now, remember our earlier session, we said that it will be helpful for you to have a calculator in the exam, a simple scientific calculator with logarithms. Well, this is where having logs come in. If you take the log of 2, that is approximately 0.3. So it becomes 10 multiplied by the log of 2, which is 0.3. It becomes 10 multiplied by 0.3. We are just working on this term here. It started off as 10 over 5, then it became 2, and then we took the log of 2 and we ended up with 0.3. Notice the 10 is continuing to be carried. So we end up with 10 multiplied by 0.3, which is 3 dB. And it's a power increase, so therefore it's positive. The second question that we just dealt with, we moved from 12 watts to 3 watts. We had a power decrease. So the first power was 12. So we are using the same formula here again to calculate dB. The formula is 10 multiplied by the log of the 2 powers. The first power was 12. The second power level is 3. So we are moving from 12 watts to 3 watts. We come down to this next equation. We simply divided 3 by 12. That's 0.25 or 0.25. So we end up with 10 multiplied by the log of 0.25. What is the log of 0.25? We use our calculator and find out that the log of 0.25 is approximately 0.6. So we end up with 10 multiplied by 0.6, which is 6. But why is it negative? Because we had a power decrease. Let's do the last one. The last one, again, using the same log formula that we have used here. It's 10, the log of the two powers divided by one another. So we are, in the question, it said we went from 20 watts to 200 watts. So that's a power increase. So we put the first power below, P1. We put the second power above, that's P2, 20 watts, 200 watts. Well, we move down to the next step. We notice that 200 divided by 20 is 10. That's how we get 10 here. Then we end up with the equation 10 multiplied by the log of the number 10. The log of number 10 is 1 when we plug that into the calculator. So we end up with 10 multiplied by the log of 10, which is 1. And 10 multiplied by 1 is 10 dB. And why is it a positive 10 dB? Because we have a power increase. So coming back to the question or questions. That's how we actually calculated 3 dB, minus 6 dB, and 10 dB using the actual formula for decibel. So just thought we'll demonstrate it to you for the purpose of the exam. You really just need to remember that doubling the power is 3 dB, or halving the power is also 3 dB, but minus 3. If you are quadrupling the power, or a ratio of 4 to 1, it's 6, but it's minus 6 because it's a power reduction. And if you're multiplying, or the ratio is 10 to 1 or 1 to 10, it's 10 dB. Whether it's positive or negative, it depends on whether you have a power increase or a power decrease. So we just need to learn these three things: 3 dB, 6 dB, 10 dB, one being double, quadruple, 10 times, or half, quarter, 1/10. Once you learn that, you'll be good for the exam. So we just have a couple minutes left, and we will just introduce you to the next topic on the curriculum, electronic components. We could do a couple of them quickly because you would have encountered these in a previous class when we dealt with circuits. So they are telling us what a resistor is. Remember, we were using the analogy last couple of classes that, yes, we're talking about an electric circuit, but for us to understand, we try to make an analogy with water. So we say that a resistor is a component that opposes the flow of current. So think of a resistor like a lock-off valve in your water system, or a tap. As you close the tap, it presents more resistance to the flow of the water. So a tap is like a resistor in the circuit, except that a tap, you could turn it, open it, and close it, and therefore that would be like a variable resistor. What do we do? Because it opposes the flow of current, what is a resistor used for? We use them to control how much current flows. If it opposes flow of current, then we can adjust it to control the flow of current in a circuit. And because we had looked at Ohm's law earlier, Ohm's law tells us that the higher the resistance, the lower the current. Most resistors will have a fixed value. And what is the unit of resistance? We learned before was the ohm. However, some resistors are variable, just like in your tap. When you open the lock-off valve halfway or you close it, it's variable. You can apply varying amount of resistance in your water circuit to increase or decrease the flow of the water. Well, you have variable resistors, and those variable resistors are sometimes called potentiometers, right? So that's just another word for variable resistor. Let's go to the questions that deal with those concepts. What electrical component opposes the flow of current in a DC circuit? Well, we know that in a water circuit, it's a valve or a tap, and we know the electric equivalent of that is called the resistor. So therefore, the component that opposes flow of current is called a resistor. Again, we dealt with these concepts in lesson 1 and a bit in lesson 2. So if you need a review, please look at those videos. Next question. What type of component is often used as an adjustable volume control? What they are just simply asking you here is another way to ask you, what is a variable resistor? Because in a radio, let's say if you have your car stereo or your home radio, when you turn that little dial to increase the volume or decrease the volume, what that really is turning is a variable resistor. And what we said is another name for a variable resistor. We said it was a potentiometer. So therefore, what they're asking us is the component that is used to adjust the volume control. It's an adjustable or a variable resistor. And the term for a variable resistor is a potentiometer. That's how we get that answer. Let me ask the question in another roundabout way here again. What electrical parameter is controlled by a potentiometer? Well, you know a potentiometer is a variable resistor. If it's a variable resistor, what it controls? It controls the resistance. So therefore, the answer is resistance. Again, in the question pool, they will tell you all sorts of things that will control frequency and all sorts of other things that will tell you, but you know that a potentiometer is a variable resistor and it controls resistance. So we have come to the end of our session. I thank you very much for being in the audience today. We will entertain any questions via email. Our next class is scheduled for Friday, the 19th of June. So let us all have a great weekend. Please be safe, everyone. And we will send out an email to the link with the stream video for you to review. And again, if this is your first class or you have not seen sessions 1 or session 2, it is available via the YouTube channel, which you will get via email. So thanks again, folks. We really appreciate it. Thanks very much for your kind comments there, Anthony. And have a safe weekend, everyone. Be good, be careful, and see you for our next class. Have a good night.